Good morning, Chemistry 2341, our Tuesday, Thursday, 8 a.m. class. We only have 21 of us here, but I'm sure a lot of people are going to view this video. So make sure to do a lot of stuff in the chat and ask lots of questions so they can participate as well. Anyway, so we had our last exam. I'm currently trying to make sure I don't have an upload error because one of my other classes, it's like some people's scores were higher, some were lower, and some didn't change at all. So that's kind of weird. And so I'm going to work on that. And I'm hoping to have that updated sometime today, but hopefully you'll go and check that. Remember, the number you see in Canvas is the real number, and that's out of 120 points. So don't think, oh, I got 120 on the exam. That's great. That's an A++++. No, it's out of 120 points. So go ahead and remember that. Okay, that being said, we are going to continue on. We have chapters 8 through 11 to get through in the rest of the semester, okay? So what we're going to do is we're going to start with chapter 8, and that's reactions of alkenes. We're finally digging into real organic chemistry, but we have to keep in mind that those mechanisms we learned and the idea that energy and sterics are driving a lot of our reactions. And we're going to see that today in our reactions of alkenes. Okay, so I'm going to go ahead and share my screen. And if you have a question, go ahead and ask. I'm going to put my video gallery way over here. And you should be able to see module 8.1 reactions of alkenes. Okay, so that being said, let's go ahead and look at this. So in this chapter, we're going to learn all of these reactions, what each of this means. Okay, we're going to learn, did you unlock the textbook for this module? Good question. Let me double check that. Because I think I unlocked the homework. Let me do that because that's important for you guys to follow along if that's there. And of course, Top Hat is slow. Okay. No, module 8 is not open. Thank you. The good call. I'm going to put module 8. Okay, that's module 6. Put that way. Deselect. Module 8.1 and 8.2. Come on. I'm going to go ahead and assign those as review. And I'm going to assign the reading as homework. Homework now until next Monday at midnight. Come on. It's going really slow. Okay, stop telling me things. And let me, there we go. So this will be due on Monday, the 19th at midnight. I'll double check the syllabus to make sure that's when we're supposed to be having it, but that should do it. And 2 attempts per question, provide feedback, show correct answer after last attempt. All right, assign. All right, so hopefully I'll go back and I'll sign the rest of these for the rest of the semester according to our updated syllabus. So you should see all those available to you sometime today. All right, thank you for that comment. Okay, let's get back to this overview we see here. This overview is, these are all the different reactions we're going to learn, and it's also a lot of words we're going to be learning about. For example, syn addition and anti-addition. Those are going to be very important. And syn and anti-addition is controlled by the mechanism. So if you know the mechanism of what the addition's doing, then you know whether it's a syn type addition or an anti-type addition. So what we're going to find out is that syn is when they're going to be adding across the same side of the double bond to change our hybridization from our sp2 to our sp3. And so we're changing our hybridization. And then we're also going to learn what anti means. Anti means we're going to add one thing to one side of the double bond and another thing to the other side and the bottom of the double bond. So we're going to hit the top and bottom of that double bond. And that's what we're going to call anti-addition, okay? Now notice each and every one of these chemical reactions can be one, the other, or both. And so by knowing what mechanism we have, that's going to tell us exactly how this works, okay? So when we talk about the first reaction we're going to talk about with alkenes is what we call addition reaction. So we're going to take away the double bond and go back to sp3 hybridized carbons. So the idea is we're going to add one thing to one carbon of the double bond and one thing to the other carbon of the double bond. So in the case of adding a hydrogen halide or an acid like HCl or HBr, we're going to have the alkene act as our nucleophile because it has the lone pair available for it to go and attack our electrophile. In this case, it's the 2 electrons in our double bond. Okay, so it's a weak base, but it is our nucleophile in this. Once we do that, we generate a carbocation. And that is very important because that carbocation is telling us something about what our products are going to be. Now, once we form that carbocation, remember, we're going to want to form the most stable carbocation. So when we're looking at this, we want to think about the electronics of the system, okay? Now that we have that carbocation, we can have our nucleophile come in and attack the top or the bottom because that's an empty p orbital. So that's going to give us an idea of what to look for in our reactions here. So let me go ahead and change my tool to that. All right. So that's what we're going to be doing in our system. So if we look at the reaction coordinate diagram, what we see is our first activation energy is the formation of our transition state. That's where our group is starting to leave. I'm sorry, that is where our electrons in our double bond are reaching out and grabbing that hydrogen. And then that's decaying down to our carbocation, okay, which is our intermediate. And then our reaction of our carbocation with the nucleophile is the second transition state. And then overall, the reaction is always exothermic because we go from a double bond, which is storing potential energy, to all sigma bonds, which is always lower in energy. Okay, so when we think about this, we also want to think about the order of reactivity of this because of the acidity. The more acidic the hydrogen, the faster it's going to react, which means HI is going to be faster than HBr, which is going to be faster than HCl, and that's going to be faster than HF. Remember, it's in order of acidity because the double bond is acting as our base. So the double bond, the more acidic that proton is, the more reactive that double bond is to that more acidic hydrogen. Okay, so what's the mechanism brings about a certain amount of regiochemistry. Okay, so the first thing we have to think about is that not all chemical reactions have a specific region where they're going to react, but hydrohalogenation means it's going to react in a very similar fashion almost every single time, okay? And in this particular reaction, the hydrohalogenation reaction, we have what we call Markovnikov's rule, okay? Now, in Markovnikov's rule, we have the hydrogen always adding to the carbon with more hydrogens. Write that down. The hydrogen always adds to the carbon with more hydrogens. And I'll tell you why. Because in the formation of that bond, you form a carbocation. You want to form the most stable carbocation possible, and that means it's going to be the more substituted with carbon bonds. So whenever you have a choice between one carbon and no carbons, it'll still try to make that secondary carbocation. If you have the choice between a tertiary carbocation and a secondary carbocation, it's going to make the tertiary carbocation. This stability of the carbocation gives rise to the regiochemistry, and we call it Markovnikov's rule. So the one with more hydrogens always gets the hydrogen, and then then whatever the conjugate base was, whatever the nucleophile becomes after that protonation, like the bromine, will always go to the more substituted carbon because it's reacting with that carbocation. Okay, so if we look at the mechanism, we have a choice of adding it to one of the carbons or the other. It's always going to add to the carbon with that'll form the more stable carbocation. which means our product is always going to be the more substituted alkyl halide. So, and it has everything to do with that stability of the initial transition state, that activation energy to form that partially positive carbocation on that less substituted carbon is higher than trying to form it on a tertiary carbocation, and the product forms is less stable than that. So it's a higher activation energy, so it's a much slower reaction, and it makes a less stable product, so it's less likely to happen. So you want to think about it from an energy perspective. It's easier to form a tertiary carbocation, and therefore it's the major product from our reaction. And then once you form that tertiary carbocation, it's going to react with the remaining bromide to create that more substituted halogenated product. Okay. So, questions on hydrohalogenation. It's a very common reaction. Remember, we made alkenes by removing an H and a Cl with a strong base. This is the reverse thing. We're going to actually make the more substituted material. So this is a cool reaction if you started with a primary alkyl halide, but you wanted a tertiary alkyl halide. You treat it with base to create your alkene, and then you would treat it with acid to generate your more stable carbocation, which gives you more substituted alkyl halide. So that's one way to look at it. Well, you know, that's not the only thing we have that we can do. So we also have what we call acid catalyzed hydrolysis. Okay, so we're going to add water across that double bond. So we're going to have an OH on one side and a hydrogen on the other. Okay, so whenever we have an acid catalyzed system, the first thing we're going to do is we're going to protonate something, right? And in this case, we're going to protonate the water to give us a hydronium ion. That hydronium ion gives us a very acidic proton, which then can add to the alkene and give us our intermediate. Notice it also gives us a carbocation intermediate, which means acid catalyzed hydration follows Markovnikov's rule. The hydrogen is going to go on the carbon with more hydrogens, and the OH is going to go on the more substituted carbon. Okay, so when we look at the mechanism here, we've created our hydronium ion. It's going to react. It'll always form the more substituted carbocation. And then our water can now act as our nucleophile because we have a carbocation and create our oxonium ion here, which we can then use water as our base to get us to our neutral new alcohol, and we've regenerated our catalyst. And then this can go back up and start the whole cycle again. Okay. So again, the key feature here is the addition of the hydrogen to the carbon with more hydrogens on it to create the most stable carbocation, and then water comes in to react at that carbocation site. Okay, questions about that? Okay, now what does that mean about the regiochemistry of this? So we have that is going to always have it substituted at the more substituted carbon, but what does this make it? Does this make it a syn addition? Is it adding to the same side of the double bond, or is it adding to the opposite sides of the double bond? In this case, this is a mixture of syn and anti because you form the carbocation. And remember, your carbocation is flat. So you can have your water come in from the top to make a syn addition, or you can have it come in from the bottom to make the anti addition. So whenever you form a carbocation in your addition products of your alkenes, you always have a mixture of syn and anti addition. Okay, so remember, syn addition is where we're adding to the same side of the double bond. Anti addition is where one goes to the top of the double bond and one goes to the bottom of the double bond. Okay, so when we think about the acid catalyzed hydration, we actually have a reversible reaction. Okay, the more water you add, you drive it to the alcohol. And if you somehow remove the water or have more acid in the system, you can actually dehydrate. So this is a reversible reaction, and you can make it go back and forth just by adding water or removing water from your reaction. And remember, when we did that reverse reaction to make alkenes, we protonated the alcohol, and then it made it a good leaving group, and then we could remove the hydrogen and have those electrons come in and form our double bond. Okay, so that's just the mechanism we're looking at. All right, so we've done hydrohalogenation. We've added an acid across our double bond. We've done hydration. We've added water across our double bond. Okay, now we're going to have a different mechanism here. Our different mechanism is going to be halogenation. Okay, now chlorine is much too reactive and iodine is not reactive enough. So this almost always works with bromine and chlorine. Okay, and we usually use a solvent that doesn't react with bromine and chlorine. So you'll see this solvent right here. See how it's already halogenated? This does not participate in the reaction. It's just the solvent, because if it could be, if that solvent could be halogenated, it would react with the solvent and our substrate. So we always try to use a halogenated material. Okay. So what happens in our reaction? Well, we're going to add bromine across the double bond or chlorine across the double bond, meaning we're going to get a halogen on each side of that double bond. But is it syn and anti? Okay. So I'm going to prove to you that this is an anti-only addition product. Okay. So let's figure out how we're going to do this. Okay. So the first thing we need to do is we need to think about our alkene as our nucleophile. And when our alkene is our nucleophile, it's going to polarize the bromine-bromine bond to give us a reactive species. Okay. So the first thing that happens in that system is the alkene comes in close proximity to the halogen, the bromine-bromine or the chlorine molecule, and it starts to polarize that bond. And when it polarizes that bond, it creates the bromonium or chloronium ion. And it does this by actually sharing both electrons of the double bond between the halogen here. So we form this three-membered transition state, okay? And with bromine, it's bromonium ion, and it's the major resonance contributor to the system. But why? Why would we do that? That's such a small thing, you know? Well, it turns out that it's, when we're using both of those electrons from the nucleophile to connect to that electrophile, it makes it easier to share those electrons and form that positive charge temporarily. Okay, so it's an energy driver. Now that we have that bromine sitting on top of our double bond, we now have the bromide ion. Notice we generated the bromide ion when we formed that structure here, is now acting as a nucleophile. But the top is blocked by that two bonds to bromine. It has no choice but to go to the bottom of the ring, or the bottom of the double bond in this case, and it's actually locked in place in a ring. And that means we must have what we call anti-addition. First bromine one on the top, second bromine one on the bottom. That's our only product we get. Now in this case here, because of the anti-addition, we actually end up with enantiomers of it. Because it's locked in place in that double bond, if it was a straight chain, it would just be two bromines, but it would still give us an anti-addition. Okay. So, but unlike the alkyl halide, unlike the acid adding across there where you form the carbocation, we don't form that carbocation. And we know we don't form that carbocation because we do not get any of the syn addition product. There's no syn addition product, ergo there is no way we went through that carbocation. We must have gone through this bromonium bridge, and that gives us our anti-only product. Okay, questions on that? Okay, so it's really important to think about the mechanism to figure out whether it's a syn addition, same side, or anti-addition, opposite sides on this. So we've added acid across there, it made a carbocation. We've added water across there, it made a carbocation. We added chlorine and bromine across it, and it makes a three-membered ring that's a cation. Because that three-membered ring drives us to form the nucleophile coming in from the other side, we now have a regio-specific reaction. All right, so what if we did this reaction with this bromine, and instead of using a halogenated solvent, we did the reaction in water? Water can't be halogenated, okay? Well, we end up with a different product because water can also act as a nucleophile, okay? And we call that the Halohydrin reaction, okay? So if you do the bromination in the presence of water, we have enough of our weak nucleophile water to come and react and give us our bromine on one carbon and then our OH on the other carbon, okay? And so we call this the halohydrin because we have an alcohol with a halogen one carbon over. Note, we still go through the exact same intermediate with the bromonium ion, that three-membered ring, and therefore it's anti-addition only. And depending on the concentration of bromine and the concentration of water, the major product is typically the halohydrin, which is the alcohol with the halogen, but you might get some minor product of the addition product with bromine. Now note, each of these, because we're locked in a ring, we're going to get a pair of enantiomers, okay? So this is not only regio selective, it's also stereo specific, okay? So it's going to react with the bromine at one site and the OH at the other site, and it's going to be top and bottom. Okay. So what if we have an unsymmetrical alkene? Is there still regiochemistry? Yes, there is. And the reason there's regiochemistry is because in the case of an unsymmetrical alkene, those two carbons are not exactly the same, and therefore they don't have the exact same bond nature to each of those carbons, okay? So let's look at this one right here. We have two carbons on this side here and no carbons on this side here. And if we were to create our bromonium cation or a chloronium cation right here, we would see that the bond to the less substituted one is going to be stronger than the bond to the more substituted one. Why? Remember, carbocations are more stable. That means that partially positive charges are also more stable on the more substituted carbons. That means that the bond between that more substituted carbon and the bromine is longer and weaker than the bond to the less substituted carbon. And if it's longer and weaker and has more of a positive charge, now we have a preference. It can go to the carbon with the greater positive charge because we have a weak nucleophile. And in this case, we're reacting with alcohol. And we see that we get specifically reaction of the oxygen at the more substituted carbon. So we actually now have regio-specific chemistry based on the stability of our carbocations. So we need to think about that in the system as well. But notice, because we're forming that three-membered ring, it's still an anti-addition, and it's forming in a Markovnikov's-like fashion, meaning the second one is coming in on the more stable carbocation. Okay, the first thing that came in is going to be on the least substituted carbon. The second thing coming in is going to be on the more substituted carbon. So it actually follows Markovnikov's rule. All right, questions on that? Okay, so we've added acid, we've added water, we've added halogens and water, and we just showed that you can replace that water with an alcohol to create an ether instead. We also need to remember that we have regio-specific chemistry. The hydrogen's always going to go to the more the carbon with more hydrogen. The nucleophile is always going to go to the more substituted one. And in the case of our formation of our bromine, we have anti-only addition because we're blocking the top of our alkene. Okay. So We have a lot of things to pay attention to here, and we want to make sure that you get those straight in your head. Okay. So if the formation of this partially positive carbon gives us regiochemistry with atoms that have a high electronegativity. What if we react it with something with a lower electronegativity than carbon? If we react it with something with a lower electronegativity than carbon, we should be flipping the regiochemistry. So let's think about what has a lower electronegativity than carbon. Well, carbon's here, so if we move over on the periodic table this way, we have nitrogen, oxygen, and then halogens. So those are all going to react Markovnikov's fashion, okay, because these are all more electronegative than carbon. But what if we move the other way? Ooh, we have bromine, sodium, lithium, things like that. A lot of the metals, like mercury, these are all less electronegative than carbon, meaning that the negative charge is going to be on carbon. So instead of having that partially positive, that positive or partially positive charge on carbon with the more electronegative atoms, we're going to shift it the other way. We're going to try to form the partially negative charge on carbon. And that's what happens when we do a reaction with boron. I'm going to talk about the hydroboration oxidation. Okay. When we do hydroboration, we have a thing called borane. It's boron hydrogen, and it's usually done in a complex with a solvent. In this case, it's THF, tetrahydrofuran. And the boron is less electronegative than carbon. Okay, which means if there is a choice, the boron is going to take on the bond with the less substituted carbon. Okay, the boron is going to add to the less substituted carbon. So it's the reverse because of that electronegativity difference here. And in the case of boron, it has 3 different hydrogens that it can use. And so it's going to add across the double bond where the boron's on the least substituted carbon. And then it's going to exchange the 2 more hydrogens. And you actually end up with this big complex right here. It's this trialkyl borane. Now that trialkyl borane is a stable compound. However, if we oxidize the carbon-boron bond, we can end up getting an alcohol on that carbon. So what does this mean? We're going to get our alcohol on our less substituted carbon. Okay, that's backwards from just the acid catalyzed hydration. Acid catalyzed hydration will always give you the alcohol on the more substituted carbon. Hydroboration oxidation always gives you the alcohol on the less substituted. So now you can selectively choose whether you want your tertiary alcohol or your primary alcohol by choosing your reagents. Okay, if you want your tertiary alcohol, just add acid and water, boil it up. If you want your primary alcohol, you have to do your borane reaction and then oxidize it with this peroxide in base and water. Okay. Okay. So it has everything to do with the idea that things that are on the, lower number side of carbon on the elemental table are going to try to put that negative charge on carbon, and they're going to react differently than the oxygen, nitrogen, and the halogens. Okay, so let's look at how we can do this right here. In comparison, I forgot I had this slide. In comparison, we can selectively choose to get our primary alcohol over our tertiary alcohol. And so if we use the same substrate here, if we want our primary alcohol, we use the borane followed by our peroxide. If we want the more substituted alcohol, we just use the dilute acid catalyzed hydration. So is hydroboration stereo specific? And the answer is yes. Okay. In fact, Hydroboration is a syn addition. The boron and the hydrogen add across the double bond at the same time. Okay, so that's different. This is the first one we had that's adding across the same at the same time. Okay, so what happens is the boron lines up with the least substituted carbon and adds across the double bond with the hydrogen getting on the more substituted carbon, and then the boron is on the least substituted carbon. And then when we oxidize that off, it's just oxidizing that bond. It's not a nucleophilic attack. So that means the oxygen is on the same side of that ring as where the boron was. And therefore we get a regio selective reaction. And because the boron goes on the least substituted carbon, but we also get a stereo specific reaction because the boron and hydrogen add across the same side of the double bond. Okay, so brush up on stereospecific and regiospecific. Okay, and it has everything to do with the idea that boron is the less electronegative, and we can have the carbon form the more negative charge. All right, and so here's an interesting way to look at this reaction is the boron's going to line up with the alkene to form a complex. And then in a concerted reaction, it's going to add the boron and the hydrogen across the double bond at the same time. If we think of it as this concerted reaction, we are guaranteed to think of it as a syn addition. And so that transition state where your boron is adding across your double bond with the hydrogen at the same time gives us a good argument as to why it's always syn addition. Okay. So let's talk a little bit about the electronics. You know, you'd think that sterics might play a role here, and they do play a little bit of a role here. But the important part is that as the boron forms this anti-Markovnikov product, we're actually going to have a little bit of an electronic effect in our sterics because the boron is gaining the electrons from the alkene, and the electrons from the hydrogen are going to the other side of the alkene, giving us a more positive charge on the more substituted carbon. But wait, hold it. We put hydrogen on the less substituted carbon when we added just hydrogen by itself. That's when we added a proton. That's when we added an acidic hydrogen. Notice this hydrogen is bringing its electrons with it. So because it's bringing its electrons with it, that hydrogen is not a electrophile anymore. Now, because it's bringing its electrons, it's now a nucleophile. And that means the hydrogen is going to go on the more stable carbocation, which gives us that anti-Markovnikov or reverse Markovnikov role. Okay. If we did it the other way around, where the boron was going to the more substituted carbon, we'd end up with the least stable, partially positive carbon, and we don't get that because that transition state is not as stable. Let's look at sterics now. Okay, the boron with the two hydrogens on it is bigger than the hydrogen by itself. So the hydrogen here is going to want to go to the more sterically demanding side. The boron will go to the less sterically demanding side. And so there's an argument for the steric factor as well. And the Markovnikov products doesn't form because of the sterics of lining up these hydrogens with these methyl groups. But when we do it the other way, these hydrogens are only lining up with hydrogens. There's no steric repulsion. And we can easily fit that hydrogen in between these two methyl groups to giving us our anti-Markovnikov product, or the reverse of what our Markovnikov product. So there's an electronic reason and a sterics reason that lends us to this hydroboration oxidation that generates the less substituted alcohol. Okay, questions on that? So we now need to pause here for a minute. Okay, we just looked at all these reactions on alkenes, okay? And they each have a way in which their mechanism works to get a certain type of product. We have syn addition, we have anti-addition. We have some things giving us the more substituted product. We have some things giving the less substituted product. We need to make sure we make a table or some kind of way to draw it all together such that you can say, okay, this reagent is syn addition giving this product. This reagent is anti-addition giving this a product. This reagent is syn addition giving this reagent. So you might want to start building a reaction table. In fact, that's going to be our group activity in a couple weeks. And I'll put some instructions on Canvas here so you can start figuring out what a reaction table might look like. All right, so once you have that boron on there, we typically don't use it as the boron. We typically oxidize it off so that we can create an alcohol, okay? And what it goes through is we have a peroxide. It's going to bind to that empty orbital of the boron, creating an unstable intermediate, which then will add an oxygen in between the boron and the carbon bond. And then that can be hydrolyzed with water, liberating off a free alcohol. The mechanism is not really that important, but I wanted to show it to you so you could see that that's the oxygen is actually coming from the peroxide, inserting itself between the carbon boron bond, and that's the oxygen that ends up being the alcohol on your final product. Okay. Okay. So in this, the most important thing is the alkyl migrates through that understable intermediate, retaining its stereochemistry. That oxygen is just inserting in there and retains stereochemistry. It doesn't flip, it doesn't act as a nucleophile, it doesn't go to the other side. So it's an insertion in that bond, not a displacement. And so we retain that stereochemistry. And once we get that oxidized to form that completely off, we replace each of those borons with a hydroxyl group, once again, without changing the stereochemistry or regiochemistry. Again, we're inserting another oxygen in between that the boron oxygen bond, retaining the stereochemistry of the product. Okay, so if the boron adds one way, the oxygen is going to be exactly in that same stereo and regiochemistry of where the boron added across your double bond. Okay, so if boron is less electronegative than carbon and reacts in a weird way, mercury will do the same thing. Mercury is going to react backwards from Markovnikov because of that kind of a system. The mercury is going to add to the least substituted carbon, but this gives us a different product here, because in this case, the mercury adds across the least substituted carbon, and that gives us our attack by our alcohol, our nucleophile, in this case, the water, to the more substituted product. So we end up with what we call Oxymercurization Demarcuirization, and it produces Markovnikov's addition products, even though we're using a reagent that is less electronegative than carbon. So what that means is that we have one, regio selectivity. The alcohol is going to end up on the more stable carbocation carbon, and the mercury is going to end on the less stable carbon, just like boron. And when we reduce off that mercury, we retain the alcohol on the product here, and we end up taking that mercury off and adding a hydrogen to that more substitute product. So it's regioselective because of the way it adds, okay? It's also stereoselective, okay? Meaning that the mercury is going to add on one side of the double bond, and the OH is going to add anti to it, okay? So if we look at these two different enantiomers, the mercury is on top, the OH is on bottom. That's the stereospecific anti-addition. And if we look at this one, the mercury is on the bottom and the OH is on the top. That's the stereospecific anti-addition, okay? So then once we go through that, we would go ahead and reduce off this right here, losing the stereocenter here, but maintain this now doesn't have a stereocenter because it's now equal all the way around. So we, even though we created an enantiomers in the intermediate, it gives us one product at the end. Okay. So just like hydroboration oxidation was regioselective and stereospecific, our oxymercurization demercurization is also regioselective and stereospecific. But remember, the boron was a syn addition regiospecific. Our mercury is an anti-stereospecific addition reaction. Okay, so the mechanism is kind of cool in the fact that it kind of does what we saw with the bromine right here. We're going to form a stabilized three-membered ring on one side of the alkene. Once it does that, it's going to polarize, and notice it polarizes just like the more substituted one here. And we're going to get attack of the water to the more substituted side because it's the more partially positive side. And it's going to have to attack from the bottom because the mercury is occupying the top. So we have our regioselective, it's attacking at the more substituted carbon, our stereoselective because it has to attack from the bottom. Okay. And then after that water attacks, it opens up that ring and we get that partially positive carbon. And whichever side the mercury's, oh, hold it, it's erasing, sorry. Whichever side that mercury's on, the OH is going to go to the other side. And we end up with, in this case, a pair of enantiomers in our system. But notice once we reduce that off, we no longer have a stereocenter because when you go around the ring, it's going to be the same on both sides. Okay. How did we remove the mercury? Well, we're not exactly sure, but we think it has something to do with transferring single electrons or a radical mechanism. And somehow that allows the mercury to come off and the hydrogen to go on in the exact same location. The reason we say that it's a radical mechanism is it can't be a carbocation because we don't lose the stereochemistry of that set. The hydrogen always appears where the mercury was. So we know we're not going through a carbocation, so we think it goes through a radical mechanism. So we can retain that stereochemistry. All right. Oh, and the wonderful thing about mercurization demercurization is because it is anti-addition, we get our OH at our more substituted carbon where we started. We can make secondary alcohols where we couldn't do that if we went through a carbocation intermediate. If we go through a carbocation intermediate and we formed an initial secondary carbocation, it's going to rearrange to form the tertiary carbocation, and we're going to end up with our more substituted alcohol. This is why we use the mercurization demercurization, because it's regiospecific. Okay, if it has a choice of these two carbons, oops, if we have a choice of these two carbons, we have a secondary carbon and a primary carbon. Okay, which means the mercury is going to add to the primary carbon and the OH is going to add to the secondary carbon, giving us our secondary alcohol in our product. Once we remove the mercury with the boron reaction, with the sodium borohydride. Okay, so it does not rearrange to give us our tertiary alcohol because we do not go through a carbocation mechanism. However, if we took this compound here, okay, so we'd add our hydrogen over here and we get our secondary carbocation, but we do a 1,2 hydride shift to get our tertiary carbocation, and our product would actually be a tertiary alcohol. Okay, so This is where regio-specific chemistry is very important. In these reactions with the hydrolysis, acid catalyzed hydrolysis, we go through that carbocation intermediate. It will rearrange to get the most stable carbocation possible, and therefore gives us the most substituted alcohol possible. By going through the regio-specific chemistry of the mercury going on the least substituted carbon, the alcohol going on the more substituted carbon, and not going through the carbocation, we can get just our secondary alcohol. Okay, questions on that? So this is where it takes some time to write the reagents down, the products down, whether the thing is syn and anti, whether it's regio-specific and stereospecific. So sitting down and writing those out for each of those reactions and making yourself a little table is going to be very important to understanding all of these different reactions in the system. Okay. All right, so that was comparing the oxymercurization demarcuirization to the hydrolysis, acid catalyzed hydrolysis. If we compare it with the hydroboration, because the boron is going to add to the least substituted carbon, we're going to add to our alcohol to our least substituted carbon. So if we look at this hexene, we're going to end up with our alcohol on our primary carbon if we use borane and peroxide, giving us our primary alcohol. But if we use the mercury right here, Oxymercurization Democratization, we're going to add the mercury to the end here, and the OH is going to be to the secondary carbon. And then when we reduce off our mercury, that's going to be replaced with a hydrogen right here, meaning we get our secondary alcohol. Okay. So when I ask a question in the homework or on an exam, starting with this alkene, I want you to make a primary, a secondary, or a tertiary alcohol. Choose your reagents. Okay. So what you'll think about is, well, I have this alkene. If I look at this, this is a secondary carbon. And so I need to pay attention to which reagents I use. If I want to go, I have a tertiary carbon here. If I want my alcohol on here, I just have to go through acid catalyzed hydrolysis. It'll form the secondary carbocation, it will rearrange to the tertiary carbocation, and I'll get my tertiary alcohol. Okay. But let's say, no, I don't want the tertiary alcohol, I want the secondary alcohol. Okay. Then I have to go with oxymercurization demarcuirization, because the mercury is going to add to this side here, the alcohol is going to add to here, and then we're going to reduce that off to give us a hydrogen to get our secondary alcohol. But say, well, you know, I have a lot of the secondary alcohol already, and it was easy to make the tertiary alcohol. I really want the primary alcohol. Okay, it's like, okay, well, I got to use a different reagent then. I got to add the boron to the least substituted carbon, then oxidize the boron off to give me my primary alcohol. My primary alcohol. Okay, so notice that one starting material can give 3 different products because our reactions are regio-selective. All right, questions on that? Ooh, forgot to bring my iced tea upstairs. Okay, so let's talk about the next reaction we can do with alkenes. The next reaction we can do with alkenes is convert it to a reactive ether. And we had, when we talk about ethers in chapter 11, we're going to find out we have this very reactive ether, which is called an oxycyclopropane. It's also called an epoxy or an epoxide. Okay, basically it's a 3-membered ring with an oxygen on it. Okay, this 3-membered ring is very strained, and so it will pop open and react with lots of things. But the interesting thing is that we can make it very readily from alkenes. Okay, We make it from an alkene with peroxides. Okay, we're going to take either a carboxylic acid with an extra oxygen in it. In this case, it's a metachloropurbenzoic acid. The per meaning it has an extra oxygen in it. So peroxyethanoic acid is peracetic acid. Okay, so it's a carboxylic acid with one extra oxygen here. And that means that that extra oxygen, because the one for the acetic acid, the acid itself, is partially negative, that oxygen carries a partially positive charge. Okay, wait a minute. We have a partially positive charge and we have an alkene. Our alkene is a nucleophile. So what we can do is we can take that partially positive oxygen here and add it across our double bond, creating this three-membered ring to form an epoxy. And then we can do other chemistry. The most common chemical you'll see is what we call Mcpba, which is metachloropurbenzoic acid. And we typically do this in a solvent that's not easily oxidized. So this is just the solvent right here, dichloromethane, and to make this epoxy. Now, the cool thing about this epoxy is you can use it as an intermediate for doing additional reactions on alkenes. So the oxycyclopropane, I'll probably call it epoxy or epoxide most of the time, that three-membered ring. Okay. So I said we can form it fairly easily. What's going to happen is the one oxygen is going to act as a electrophile because it's partially positive. The alkene is going to act as a nucleophile, and it's going to, in a concerted reaction, either add to the top or the bottom of the alkene to generate our oxycyclopropane or our epoxy. Okay, and when it does that, it ends up being a neutral molecule and it liberates a regular carboxylic acid. So it just loses that oxygen across that double bond. Okay, and it either adds to the top or the bottom, doesn't matter which, and it gives us this reactive intermediate. Okay, but this is a cool thing because now let's tie it back to the adding bromine. We had that bromonium cation as an intermediate. That means whatever we react it with has to come in from the bottom. Whatever we react it with will have to come in from the bottom because the oxygen's blocking the top. So we can look for that source of where the nucleophile is going to come in. So if the oxygen is blocking the top, we have a concerted reaction where it comes in and does it all at once. We have stereochemistry. Okay. So if we started with our cis alkene and we added to the top here, our two hydrogens are going to stay on the same side when we form our product. So a cis alkene will make a cis-like epoxy compound. And because we, again, do it concerted across the top here, a trans alkene will make a trans-specific epoxy. Okay. And it still has that regiochemistry because it's still locked into that place because of the cyclopropane. Okay. And then, okay, questions on that? So McPba, metachloropurbenzoic acid, is what we use to add an oxygen across the double bond to create an epoxy. The stereochemistry, because it's concerted, is retained. All right. So let's look at that. So that's not really a syn addition because we're not adding two things across there. We're adding it to one side. It's kind of a concerted reaction on one side, so there's stereochemistry. So let's go back to the simplest kind of reaction. Let's take our alkene all the way down to an alkane. Okay. You can't just use hydrogen by itself. Hydrogen by itself is a nonpolar bond, or alkene's a nonpolar bond. There's just nothing helping drive the reaction right here. So we always use a catalyzed hydrogenation. We usually use a solid like palladium, platinum, or sometimes nickel. What happens is you have the catalyst surface, the metal surface, is reactive and it reacts with the hydrogen and breaks it up and bonds it to the surface of the metal particle. Okay. Now those hydrogens are activated because they've been reacted with the surface of the metal. Now that our alkene can come in and we have the alkene react with those reactive hydrogens, they're polarized and they will react with the alkene now. They'll transfer a hydrogen to one side, and then because of you're so close, because of close proximity to another hydrogen, you always get syn addition. Okay, so this is another specific reaction where we have syn addition. Imagine the alkene just coming down on the surface, transferring two hydrogens from the surface to the alkene, giving us syn addition. Okay, so the catalytic hydrogenation is a syn addition product as well. Okay, all right. So let's actually review. This is slide what? Okay, let's go back to my first slide. Okay, use this slide to help you correlate everything we just talked about. Adding the hydrogen and a halogen across there, it is syn and anti because it goes through a carbocation. Acid catalyzed hydrolysis is syn and anti because it goes through a carbocation. Halogenation is an anti-addition because we form the three-membered ring. Okay. Hydrohalogenation, Halohydrin reaction, we added halogen and OH to it, is an anti-addition because we form that three-membered intermediate. Hydroboration is a syn addition because it adds across it all at one time in a concerted reaction. In the mercury, we have syn and anti-addition because you have the mercury adding one side and the OH adding the other side, and then you can oxidize off so it actually can lose the stereochemistry. And in the case of our catalytic hydrogenation, it's also syn addition. All right, so that takes us to this. Okay. All the reactions that give you a mixture of syn and anti are the ones that go through either a carbocation intermediate or a mercury intermediate. So we have hydrohalogenation, acid catalyzed hydrogenation, oxymercurization demarcuirization. And if you don't use water, you can create an ether, and we call that alkoxymercurization demarcuirization. Okay. So those give a 50-50 mixture because you're going through a carbocation. Okay. These reactions only do syn addition. Hydroboration, hydrogen and boron being added across the double bond at the exact same time. Catalytic hydrogenation, it sits on the surface, adds on the same side. And then syn dihydroxylation we'll talk about in a minute. But that addition is also the formation of the epoxy. Okay. And then reactions that only yield anti-additions are the ones that form that three-membered bromonium or chloronium cation. Okay, so those are only anti because the top is blocked by that cation and the nucleophile has to come in from the bottom. Okay, so that's one way to help summarize the stereochemistry. All right, stretch a little bit and we're going to carry on for our last 20 minutes here. Anybody have any questions? Chat's been kind of quiet. We're up to 30, that's good. Which of the syn and anti reactions is most common? Well, it's all in kind of what you want to do. You know, it's about stereospecific, you know, do I want the primary or secondary or tertiary alcohol? So we can actually kind of trick things to go the way we want them to go. For example, if we wanted an alcohol and we want it to be a very specific place, we would choose the reaction to give us that. Okay. Which of the syn and anti reactions are the most common? I don't I don't think I can answer that question because it all depends on what product you want. So the reagent and the product and the starting material are all related to, you know, what you're looking for. Okay. Okay, so we did a whole bunch of things that were additions to alkenes. Okay. Now let's do some stuff that is oxidizing alkenes. Okay. But before we do that, we have to talk about the oxidation state of carbon. Okay. So if we think about it, we want to look at the idea that our lowest oxidation state is most like methane. Okay. Okay. Most like methane. So you have 4 hydrogens on it. That's the lowest oxidation state you can have for carbon. Okay. Now, if you go the other way, the highest oxidation state is, let's see, CO2 or something like that, where you have as many oxygens around the compound as possible, like carbonic acid or something like that. The more oxygens around it, the higher oxidation state. Okay. So that means that if we have an alkane, that's going to be a lower oxidation state than just having one bond to oxygen, which is an alcohol, which is going to be a lower oxidation state than anything with an aldehyde, and then a ketone would be a little above that. And our most oxidized system is going to be carboxylic acid. Okay. So that means that if we go from an alkane to an alcohol, we're oxidizing it. If we go from an alcohol to an aldehyde, we're oxidizing it. If we go from an aldehyde to a carboxylic acid, we're oxidizing it. And then going in reverse, we have to do the reverse. So we can choose our chemistry selectively to go just 1 step, 2 steps, or multiple steps across the system. So that's our relative range. So let's actually do a calculus, show you the math on doing that. So you assign -1 to the carbon we're looking at. So we're going to look at a carbon. We're going to subtract 1 for each hydrogens bonded to it. Okay. So that means that methane right here is our lowest one possible, because we have 4 bonds to carbon, we have 4 hydrogens, which means our oxidation state is -4. Okay. So if we have a carbon bonded to a more electronegative element, oxygen, nitrogen, or halogen, we go +1. Okay. So if we look at this carbon here, just this carbon here, right here, we have 1 hydrogen, but we have an oxygen. So we get a -1 for this, a -1 for that, and a +1 for the oxygen here. And you get 0 for carbons. Carbons are equal to each other, and therefore it doesn't change the oxidation state. So we get 0 for this. So we have -1 +1. So the net oxidation state on this carbon is -1. Okay. And if we look at this carbon here, we have 3 bonds to hydrogen. So we get -1 for each of those hydrogens and 0 for carbon. So the oxidation state on that one is -3. Okay. So the lower the number, the more reduced the carbon is. The higher the number, the more oxidized the carbon is. Okay. So let's look at something like CO2. We have 4 bonds to oxygen. So that means we get +1 for each of those 4 bonds, which means our oxidation state is 4. Okay. And let's look at this one over here. Let's look at the oxidation state of this one. We already know this one's -3 because we have 3 hydrogens and a carbon. But we have 2 bonds to oxygen, so we get -2, but we have 1 bond to hydrogen +1, meaning our net, I'm sorry, backwards. Hydrogens are -1 for the hydrogen, and +1 for each of the oxygens, giving us +2, meaning our oxidation state is +1. Okay, so that means every single carbon can be ranked from 4 to -4. Okay, and going from one oxidation state to the next is changing the number of bonds we have to hydrogens and carbons and more electronegative elements, oxygen, nitrogen, etc. Okay, so why is this important? Well, we need to know what we're doing in our alkene when we're doing additional chemistry to it. Okay. So now that we know how to calculate oxidation states, and I think there's a couple homework problems in this, by the way, we can look at changing our alkene to other things. And instead of adding just something across that double bond, we're going to oxidize that double bond with a variety of oxidants. And some of these oxidants are very specific about how they react with the bond. Some of them break the double bond completely. Some of them add across it in a stereospecific way. So the first thing I want to talk about is osmium tetroxide and potassium permanganate. Okay. The first one we want to think about is osmium tetroxide. It is a nice little, square planar system here. It has 4 oxygens on it, and osmium has a +8 oxidation state. That means that it can change its oxidation state to give up bonds to oxygen. So when we have our electrons from our double bond here, we can use those 2 electrons to go out and attack one of the carbons, kicking in 2 electrons to the osmium, and then kicking out 2 electrons from this double bond to form a compound, this cyclic osmate ester. Okay. So this is a syn addition to form 2 oxygen bonds across that double bond, and we have osmium as the complex. Now, if you oxidize off the osmium, you end up with 2 alcohols that are syn, and they're on the 1,2 carbons, right? So we have a diol, 2 alcohols, and because it's on the 1 and the 2, we call that bisynyl because they are 1 carbon apart, and it's syn addition, okay? So in this case here, we are oxidizing the 2 carbons right here by reducing the osmium. And then when we oxidize it's off the osmium back to osmium +8, we gain our free alcohols here. Okay, so osmium tetroxide will always add syn addition across a double bond to give us our vicinal diols, or our 1,2 diols. And it turns out that osmium is really, really toxic. So we rarely just use a catalytic, we rarely use just one equivalent of the osmium tetroxide to do the oxidation. We typically use a catalytic amount and something that'll oxidize the osmium back to tetroxide. Actually, it didn't, it's just reduced off to give you osmium. It's, osmium +4, actually. So what we end up doing is, we use a catalytic amount of osmium tetroxide, but then when it gets knocked off as the osmium 6, it can be reoxidized using an oxidizing agent. And one of the more common oxidizing agents is this. This is NMO, or N-methyl, meaning we have a methyl group on the nitrogen. Morpholine, which is this ring with an oxygen and a nitrogen in it. N-oxide, meaning we have an oxygen on the nitrogen here. Okay, so N-methyl morpholine N oxide, or NMO, can oxidize the osmium off and regenerate osmium tetroxide and give us our vicinal diol. Then that can be reused to react with another alkene. Okay, so this is the more common way to use it. You might see it in homework used as catalytic osmium tetroxide with NMO. But what we're doing is the exact same thing. We're generating a syn addition of 2 alcohols across a double bond. Okay, well, okay, potassium hydroxide, potassium permanganate looks a lot like the osmium tetroxide. It's got 4 oxygens around it's got 4 oxygens around the manganese, okay? So it looks like it would react exactly the same way. However, it can only do that under mild neutral conditions. The reason is the permanganate is actually a stronger oxidizing agent, okay? Instead of giving us this diol that we get with the osmium tetroxide, what it does is it actually breaks the double bond and oxidizes each of the 2 carbons down to carboxylic acids. Okay. So I said oxidizers can act on these alkenes in different ways. The osmium tetroxide adds 2 alcohols to it. The permanganate cuts the double bond in half and turns it into 2 carboxylic acids. Okay. So the difference you would see is if you have potassium permanganate and hydroxide, you're going to get the cleavage of the double bond. If you have potassium permanganate neutral cold, you can get the creation of the vicinal diol. Okay. Another oxidant we have is ozone, O3. Okay. O3 does what the permanganate does in the sense that it cuts the double bond, but instead of turning it into carboxylic acids, it turns them into aldehydes and ketones depending on what's attached. Okay. So when we look at this here, if our ozone comes in and breaks this bond, it's going to break it here. This one, because it has 2 carbons on it already, is going to turn into a ketone. And because this has 1 carbon and a hydrogen on it, this is going to turn into an aldehyde. Okay. So it's going to break that double bond and put an oxygen on each of the carbons that has a double bond. So we'll have a carbonyl on each. So one forms the ketone, one forms the aldehyde. If you have something that doesn't have additional oxidizing power, in this case, we call it a reductive workup with dimethyl sulfide. The sulfur actually picks up the extra oxygen and reacts with it so that we just get the aldehyde and the ketone. If we don't do that, if we actually use that extra oxygen and add another oxygen, we can oxidize that aldehyde down to a carboxylic acid. And this is what we call the oxidative workup, okay? Because there's an extra oxygen here and we're adding oxygen with peroxide to maintain our ketone. We're going to stop at the ketone by cutting this bond in half, but the aldehyde gets oxidized down to the carboxylic acid. Excuse me. I'm regretting not bringing my tea up today. Okay. So, and one of the cool things about the reactivity is if we draw the resonance structures associated with this, we end up with a negative and or positive charge we end up with a negative charge on one oxygen and a positive charge on the other oxygen. We call these dipole reagents because we have a positive and negative, and it's a net neutral species. It's just that it has a formal charge on, like in this case here, the 1 oxygen and the 3 oxygen each have a different charge. And when we have that over a system and when 1 and 3 are different charges, we call that a 1,3 dipole. If we have the 1 and 2 different charges, we call it a 1,2 dipole reagent. And this reactivity means it can react as a nucleophile or an electrophile, depending on your other system, things in the system. Okay. So how does it work? Well, because we have a positive charge on one oxygen and a negative charge on the other oxygen, it just acts as a nucleophile to 1 carbon, and then it uses the electrons from the double bond to balance the positive charge on the other oxygen. So we literally get an addition of the negative charge on this side, the electrons from the double bond kicking out to create this cyclic intermediate. Okay. Once we create that cyclic intermediate, now we can break the carbon-carbon bond to form the carbon-oxygen double bond, which is a nice stable bond to give us our carbonyl. Okay, but that gives us these 2 oxygens on the other carbon, which can then, we have a negative charge on this oxygen, so it can attack the carbonyl because they're in close proximity. They haven't diffused away. They're really close together. And you form this cyclic intermediate. Okay. This 5-membered intermediate is stronger because it doesn't have those 2 different bonds to oxygen. It only has 1 bond between 2 oxygens. And that's the weaker bond compared with the carbon-oxygen bonds. Okay. So this actually sets the stage for our next step, because we have the possibility of, when we break this off, if we break it like this, this side will leave as the ketone, and this side, if this was a hydrogen, could leave as a carboxylic acid. All right, so the next step is being specific about our workup. Okay, the ozonolysis will always create this 5-membered ring. Okay, and that 5-membered ring, how we work it up, tells you what your products are going to be. If you do something that is going to take away that extra oxygen such that it does not stay bonded to carbon, you can end up with an aldehyde. Okay, so let's look at our starting substrate here. Our starting substrate here is a trisubstituted alkene, which means when we form our 5-membered ring here, we'll have a hydrogen on here. If we use a reductive workup with this zinc metal, which will turn into zinc oxide, or this dimethyl sulfide, which turns into dimethyl sulfoxide, it takes away that extra oxygen, which means only 2 of the oxygens are transferred to the carbon, and we end up with a ketone for the one side and an aldehyde for the other side. What if you have a 1,1 disubstituted alkene? Okay, we're still going to get an aldehyde, but it's going to be the simple aldehyde of formaldehyde because there's 2 hydrogens there if we use a reductive workup. Okay, if we use an oxidative workup, we do not get rid of this extra oxygen. It stays on the carbon, and we end up with a carboxylic acid in the end. So if we use zinc or dimethyl sulfide, we get aldehydes possible. If we oxidize it down, we get carboxylic acids and ketones are only possible. Okay, let's see where we are, 16. And so let's just simplify this a little bit. Okay. When we think about oxidative cleavage or by ozonolysis, we want to say, okay, I'm just going to chop that bond in half and make those carbonyls. Okay. If I chop those bonds in half and make them carbonyls, and we have a reducing workup, that means that hydrogen stays. And we'll end up with just the 2 parts, basically pulling that double bond apart and adding 2 oxygens to it. In a reductive workup, we get that. Okay. In an oxidative workup, we do the same thing. We start there, we put the carbonyls in, but we know this aldehyde will be oxidized, okay? Which means the next step is actually taking that aldehyde down to the carboxylic acid. So the easiest way to do it is to chop it in half and draw this half as a ketone, draw this half as an aldehyde, and then say, what's the second step? Is the second step reducing, or is it oxidizing? If it's reducing, leave it as the aldehyde. If it's oxidizing, convert it to the carboxylic acid. Okay, let's see, what's my next slide actually? Oh, no, don't want to do that. All right, I will stop here and we will pick up with the anti-Markovnikov's addition of bromine via radical mechanism next time. Okay, I'm going to go ahead and stop recording. You can stay behind and ask questions if you want, or you can head out to your next class. Let's see, stop share.